Hi, good day guys. I'm Anisa Moses. This is Abbygail Steeling, Adigun Alexander, and Lashaun Simon. Right. So today we'll be doing the autonomous braking study. This project is based on the speeding and stopping distance of our vehicle when a load of 10 to 30% of its weight is applied. The initial weight of our vehicle is 844 grams, which is 0.84 kilograms. So, the vehicle will be starting at rest, which is 0 meters, and it will be allowed to travel along a distance of 5 meters. At this 5 meter point, power will be cut to the vehicle, where the vehicle is allowed to decelerate until it comes to complete rest. This distance will be measured experimentally. Now, in order to derive our mathematical models, which will describe the speeding and stopping distance of our vehicle, we will need to know our input variables. Now, input variables. One of our input variables will be u, which is the initial velocity. This will be 0 meters per second. Because we know our car starts off at 0. Our second input variable will be time, which is the time taken for the car to cover the 5 meter mark. This will be denoted in seconds. And the final one, acceleration. Now, in order to determine the acceleration, we went about using the equations of motion. V is equal to u plus at. V squared is equal to u squared plus 2as. This is our final velocity. Our initial, which we know. The time taken, this will be determined experimentally. And this is our distance, which we know, which is 5 meters. Now, for example, what we'll be doing is, let's say we run the test and we discover that the car takes 3 seconds to cover the 5 meter mark. So basically it will be this. V is equal to 0 plus A by the 3 seconds. Right? And then v squared is equal to 0 squared, which is u, plus 2a, we don't know a, s is 5 meters. So therefore this boils down to v is equal to 3a and v squared is equal to 10a. From this, we can determine acceleration by solving it simultaneously, right? So, this implies that we can get, since v is equal to 3a, we can substitute in here, v squared. So therefore, we'll get 3a squared is equal to 10a. 3a squared, so this would be 9a squared is equal to 10a. So therefore, 0 is equal to 10a minus 9a squared. Factorize. A is equal to 10 minus 9a. This denotes that a is equal to 0 or a is equal to 10 over 9. Equals to 1.1 meters per second squared. Now, we know the acceleration of the car, right? So therefore, to derive our mathematical model to determine the speed of the car, we will be using v squared is equal to u squared plus 2as. We found a previously. So therefore, v squared is equal to 0 squared plus 2 by 1.1 by 5. So therefore, v squared is equal to 11. So So therefore, V is equal to the square root of 11, which is equal to 3.3 meters per second. So actually, over the 5-meter mark, our car will be moving at a velocity of 3.3 meters per second. And this model here will determine the speed of our vehicle.
Feet, 0.5 inches.
Feet, 9.8 inches.
Hi guys, these tables on the board here show our values from which we obtained for 2 consecutive tests where we got our velocity, our acceleration, our deceleration, and the distance the car took from 5 meters to rest. Here I proceeded to show a calculation of how we found our final values in which we use for our simulations. For our new acceleration, we use the value from the first table, which was 1.16 plus 1.28 from our second table, as you can see. And we divided it by 2 in order for us to get 1.22 meters per second squared. We did the same thing for the new velocity, the new distance, and also the new deceleration.
Hi guys, today I'm going to show you the distance versus time graph and the velocity versus time graph for each load. Now these values that were plotted were found previously. Come let me show you. So, as you can see here, the graph initially started at 0. This is because the car started at rest. Now, the car was driven over a distance of 5 meters, as you can see here. At this point, it was recorded that the car traveled over a period of time of 2.93 seconds. After this, when power was cut to the car then decelerated over a distance of 5.05 meters. It took 5.4 seconds to come to complete rest. Now, as you can see, for all the distance time graph, they all were very similar. Now, let me show you the velocity time graph. As you can see, it started back at 0. Then the car traveled over the 5 meters at a velocity of 3.41 meters per second. Then it decelerated over a time of 5.05 seconds. That is why we got this shape. As you can see, for each velocity time graph, the shapes are similar.
So, after consecutive tests were done, we realized that the force on the motor was inconsistent. What I decided to do was go across to Excel and create a program. Have a look. The equation of a line was developed so that we can get acceleration and deceleration when any load is applied to the vehicle. The equations here and the other one here. The X on this point here as well as the other one denotes any mass that you would have added to the vehicle. This program shows the velocity and stopping distance for any mass percent added to the vehicle. So then it is here and the stopping distance here. And what we will do at this point is input the value. Let's say you have like 23% mass percent and you press enter. You will have the calculated velocity as well as the stopping distance here. So, for example, let's say we do an experiment of a fixed mass on the vehicle, and we have a stopping distance of 5.1 meters, and we realize that it's higher or lower than the expected. What we will do is tweak the model by using if statements on Excel, and the expected value will be calculated and outputted.